So in this video, I just want to look through some of the stuff that we have to do. In the next video, I'll do an actual example. But in this one, I'm going to look at the formulas, and then we're going to look at conditions. So confidence interval formula. So I'm actually going to look at kind of two. One for if we just happened to know the population standard deviation, where we could actually use a normal model, and then how that formula changes and looks if we only know the sample standard deviation, meaning we have to use a t-model. The formulas are going to look very similar. We're just going to kind of change small, slight things. So I want you to see that difference. So our general formula for confidence interval that we learned before is we have our statistic, and we add and subtract. Our margin of error consists of a critical value times a standard error or standard deviation of the sampling distribution. So that's our basic formula for a confidence interval. So our statistic right now, because we're dealing with numerical data and I'm estimating a mean, my statistic would be x bar. My critical value, if I happen to know the population standard deviation, I'm okay to use the normal model. So my critical value would just be a z star. And then my standard error, and this is going to go back to the formula chart. I'll show you next time where that's at, or if you remember back to when we did sampling distributions with means, our standard error was basically the original standard deviation divided by square root of n. So this is our standard deviation of the sampling distribution. So this right here would be our formula if we happen to know the population standard deviation, which is sigma, which is really not going to be the case in most situations. So let's look at how that would change if I only know a sample standard deviation. So I know there's a lot more variability, and I need to account for that. So I'm still going to start with my statistic, my x bar. That doesn't need to change. But now, instead of a z star, I'm going to use a t star, because that is what I'm going to be using in the problem. I'm using the t distribution. My general idea of a formula for standard error stays the same, but of course I don't know the true standard deviation, so I'm going to use S, which is the sample standard deviation, over square root of n. And that is the formula that we'll use pretty much always on our means problem. So it's the same idea. We're just kind of plugging in, realizing that we're using t instead of z, and we only know the sample standard deviation, so that's what we're using here. So that's our formulas. And next, I want to look at our conditions for inference, confidence intervals, and hypothesis tests for one sample problems with means. So the first condition is going to feel and seem very familiar because it is. We need, or be able to assume, a random representative sample, like always. Secondly, 10% condition, right? We want to make sure that as we're taking our sample, that things aren't changing too much between samples or between trials. So our sample size needs to be less than 10% of our population. Now, I will say for means problems, still applies, still a thing, but honestly, it can generally be pretty obviously assumed because sample sizes are a lot smaller with means problems. So it's not always as important to check. So usually on AP exam, on a means problem especially, 10% is not something they're going to count off for if you miss it. So if you're going to kind of miss a condition, this is one to skip. So for this unit, when we're dealing with means, I'm going to kind of let you off the hook on this one. It's never wrong to check it. So if you want to kind of be in the habit of it and don't want to change that habit too much, keep checking it. No one's going to take off points for that. But I am going to officially let you kind of skip this one, let you off the hook on it from here on out. But just know that it does still for sure apply. It's still there. It's just not quite as important on these types of problems. That leads us to our third condition. So our third condition is the one that checks, normality. In this case, t-ality, I don't know. We still need it to be kind of that roughly symmetric unimodal shape. So while we may not be using the normal model, we still need to check this condition to make sure the shape is going to be acceptable. So there's actually three ways that we can check this with a means problem. This goes back to, if you remember, sampling distributions and how we kind of checked for normality there. So the first way is, were we given that the population is roughly normal? So if they told us from the get-go that the heights of all people in this high school are roughly normal, or that the weights of these widgets for all of the widgets produced by this company are roughly normal. So if we're given that the population is normal in the problem itself, that is all we need. any sampling distribution coming from that population is also going to look roughly normal. So if we were given that, we can just say given population distribution is normal, done, moving on. But if we're not given that, the second thing we can look for is sample size. So this goes, again, back to sampling distributions. The central limit theorem said that if your sample size is bigger than about 30, the sampling distribution will look roughly normal even if the population wasn't. So that's the second way I can check this. Is my sample size bigger than about 30? Because if so, then I'm good by central limit theorem to assume normal model is going to work for this problem. But if not that, if I don't know the population is normal and my sample size is not bigger than 30, my last resort is to draw a dot plot or a histogram or a box plot to draw some type of graph of our sample data to see if the sample data looks sort of roughly normal. Now we're going to be very, very kind of lenient here because we are dealing with a sample and it's a pretty small sample. It's less than 30. And we can't expect a sample to look exactly precisely normal, even if the population was exactly precisely normal. So really we're looking for, is this enough for us to assume that our population was roughly normal? Do I have enough information from this graph to assume that my population was normal? So I am kind of taking a jump here, but the kind of key idea is if I see any major outliers, if there's one point that's really far from the rest of the points, that might tell me that my population is actually skewed, not normal. But as long as I don't see any major outliers on that graph of sample data, then that's enough for us to take that jump, take that leap and say we can assume our population is roughly normal. And that's really all we're looking for. So we're going to be very lenient if we check that if that third way is how we're going to have to check it. And we'll kind of see that in the problem that I do on the next video, actually looking at example and going through all the same steps of a confidence interval that we always do. So that is what's next.